Hello everyone, my name is Todorovikj and I will present our paper Predicting Algorithmic Complexity for Individuals. This is a pre-recorded presentation for the 2022 International Conference on Cognitive Modeling. An algorithm is a set of well-defined instructions to be followed in order to solve a specific class of problems. The comprehension and formulation of algorithms is part of the computational thinking research. Here, we're interested in algorithm simulation. Specifically, we want to use complexity metrics to model the difficulty that an individual has when deducing an algorithm solution. We conducted an experiment within a railway environment. Participants saw 3 train tracks like here. The top left track has a series of wagons in a specific order. They were then presented with one of these 4 rearrangement algorithms and asked to simulate the algorithm and deduce the outcome or the final order of the wagons on the top right track. We distinguished between 3 code blocks: move, an instruction to move a wagon from one track to another; while, indicating that instruction should be repeated while a condition holds, a while loop; and repeat, a for loop, indicating that instructions should be repeated for a determined amount of times. Participants solved a total of 8 tasks, 4 algorithms, each applied once to 4 wagons and once to 6. We introduced 7 complexity metrics. We first have depth. It is based on the depth of the nested loops in a code. Then we have structure, which mimics the relation between the length of a code and perceived level of task difficulty. Then we have moves, which is the number of wagon moves that the algorithm will perform. Commands counts the number of times each block is executed, and it acknowledges possible costs for checking whether a loop condition holds. Context represents the people's limitation to attend to only one context in their working memory. A context is operating on one pair of tracks. Switching between move instructions means switching contexts. Signature imitates the repetition effect. It shows that an individual needs less time to perform a repeated task. Here we assume that once an individual has processed a command once, the repetition within a loop should be easier. And finally, we have entropy as a metric. Entropy is used to quantify uncertainty. Here we take the distribution of the wagons over all 3 tracks. A higher value indicates a more chaotic distribution, potentially increasing the difficulty. We measure the correlation between these metrics and the correctness of individuals' answers. We find 3 significant values for depth, signature, and entropy. These significant correlation values indicate that these metrics should be the best predictors of answer correctness. We want to determine whether this holds on the individual levels. Are the metrics good predictors of task difficulty for each individual in our dataset? We use the C-COBRA framework to model human reason behavior on the individual level. We did a coverage analysis, which allows models to fit on each individual participant, and then we see the model's ability to represent the participant's behavior. We created the models by equipping each metric with a complexity threshold. This represents the maximum complexity that an individual can handle. We then fit the model's thresholds to each individual. When a model is queried for a prediction, it compares the individual's threshold to the task complexity according to the metric. If the complexity is too high, then it is predicted that the individual will not solve the task correctly. As a performance lower bound, we implemented a baseline model which always predicts the participant to give an incorrect answer. Here we can see the accuracy values for each complexity metric in the table, and the box plot tells us how good the individual participants are predicted. All models achieved an accuracy above 80% and performed better than the baseline model. The best performance is achieved by entropy, closely followed by structure with an accuracy of around 87%. So entropy confirms the assumption that a more disorganized distribution leads to more difficulties remembering the wagon's positions and then readjusting them. Entropy showed a significant correlation, but structure did not. Signature had a significant correlation, and it has a rather high average accuracy of 86%, but as we see here, it did not manage to cover the individuals as well as the other metrics. Finally, the depth metric, it had a significant correlation, but it is the worst predictor here. With these results, we show that we can analyze the capability of metrics to act as predictive models of task difficulty beyond statistical analysis. Thank you for your attention.